All right, good morning, ladies and gentlemen. And for today's video, we're going to talk about the conditions for sampling distributions of sample proportions, which was the question that I posted as an assignment yesterday. So we're going to talk about what the conditions are and exactly what they do for us. Okay, so before we get started, though, it is important to understand the relationship between sample proportions and also the binomial random variable. So let's say that we have a random variable x, which represents the count of successes in n independent trials. All right, so that's our random variable. We're counting the number of successes in n independent trials. Of course, as long as a random variable is defined in this way, then we know that this is the definition of a binomial random variable, where, of course, we need to ensure that there are a fixed number of trials, and this value p represents the probability of success in any individual trial, and that probability of success does not change. All right, so these are our assumptions. We're assuming p is consistent for each trial. There are a fixed number of trials, and each trial is independent of the last. Okay, now if certain other conditions are met, we can actually take our binomial random variable and say that, hey, this binomial random variable can be approximated by the normal model with a center or a mean of n times p and a standard deviation of radical npq. So we could approximate binomial random variables using the normal model with this center and this spread if certain conditions are met. Now, what are those conditions? Well, we'll get into those in a moment, because it just so happens that those conditions are exactly the same as the conditions we need to check for the distribution of p hat, right? The reason is p hat is very closely related to x. So if p hat represents the proportion of successes in n independent trials, well, then we can calculate p hat by just taking the random variable x, so the number of successes in n independent trials, and dividing by the number of successes. I'm sorry, and dividing by the number of trials. And therefore, p hat is simply your binomial random variable divided by n. And therefore, we can come to the conclusion that if conditions are met, then p hat can be approximated using the distribution of p hats, I should say, the sampling distribution of p hats can be approximated using the normal model with a center of p, and again, that's the mean. Right? And look, all we did was we took the mean from the binomial normal approximation and we divided by n. Okay. And the standard deviation of the distribution of p hats, or in the context of sampling distributions, we say standard error, but it's the same idea, is radical PQ over n. And that's simply the standard deviation of the binomial random variable divided by n. All right, so that's the relationship between these two variables, and the conditions that we state for the sampling distribution of p hats are as follows. A, we have something called the success failure condition. And so that is, we want n times p to be greater than 10, and we want n times q to be greater than 10. Now, what that does for us is it guarantees that the shape of the distribution of p hats is approximately normal. All right, so this is a condition that is geared towards our shape. Let me use a different highlighter. So we're talking shape here, and of course, the shape is normal. Now let me show you why this is using this example. And you might have seen this in a previous video, but if not, I'm just going to go through this quickly. What I have here is an Excel file of a binomial random variable. There are 40 independent trials, and the probability of success is 0.9. Now, when I go to the distribution of this binomial random variable, which again is, as we saw, related to p hat. So if I show you this for a binomial random variable, this information also applies to p hat. So if the probability of success is 0.9 and the number of trials is 40, n times p is greater than 10, so that works out. But n times q is less than 10, and so that does not work out. And so let's see what happens as a result. As you can see, the distribution is shifted way too far to the right. And as you can see, the last possible value for X is 40, which makes sense. If there are 40 trials, there can be at most 40 number of successes. However, if we tried to fit a normal curve to this distribution, there would be way too much area in the values that are above 40, and thus a normal curve would not be an appropriate shape for this distribution. Well, what happens if we adjust the probability of success to 0.1? And this fixes the n times q. N times q is now greater than 10, but n times p is less than 10. So what happens to our distribution? Well, if it's harder to get a success, then of course the distribution of the number of successes will be shifted much lower. In other words, it'll be more likely to get fewer successes. But the problem here is if we try to fit a normal curve, the right tail is no problem, but the left tail is a problem now. There's a lot of area in the negative numbers, and of course that can't happen because we're counting number of successes. You can't have a negative number of successes. So again, a normal shape is not appropriate. However, let's say the probability of success is 0.4. Now we have a situation where n times p is greater than 10 and n times q is greater than 10. When that occurs, our binomial distribution is shifted in such a way that, no, it's not dead center, and that's okay, but it's shifted in such a way that there's enough space between the lowest value. Let me rephrase this. The distribution is placed or located in such a way where if we were to fit a normal model to this data, there's very, very, very little area underneath the left and right tail that exists in the negative area of the number line, and also that exists in the area of the number line that's above 40. In other words, using a normal model fit to this specific distribution would work well because there's such a low proportion of negative area and there's a low proportion of area above 40. So when n times p and n times q are both greater than 10, this is the result. We will have a distribution that's sort of centered in such a way that a normal shape is appropriate. Okay, so there's that condition. That condition specifically speaks to the shape of the distribution. The second condition for the distribution of p hats is a random / representative sample. So why do we want this? Well, the reason is that what it will do is that it will ensure upon repeated sampling. So if we were to take many random samples, we would obtain what's called an unbiased estimate of the population parameter. In other words, this ensures that our sampling distribution will be centered at P. So, and when I say center here, I'm referring specifically to the mean of the distribution. So the representative sample, the random / representative sample condition guarantees us our center. All right. And finally, the 10% condition. So this condition, along with randomness, because of course, if we were to just use some sort of, what's it called? One second. All right. So yeah, if we were to use some sort of like convenience sample, then we can't guarantee independence based on a convenience sample. But if we have a random sample along with this 10% condition, which is the condition that says that our sample is no more than 10% of the overall population, this allows us to obtain independent samples. Why is that important? Well, upon repeated sampling, if we have independent samples, in other words, if this condition is met along with randomness, it will result in a specific spread of the distribution of p-hats. And when I say the word spread in this case, I'm referring to standard deviation, or in the context of sampling distributions, that's standard error. So the 10% condition is the item that guarantees us our spread of radical PQ over N. All right. So those are the three conditions. And what I really hope you take away from this video is that the three conditions, each one plays its role um, in describing or in guaranteeing us one of the three important aspects that we use when we describe quantitative distributions, right? The center, the shape, and the spread. All right, so that's why we have these conditions in there. These conditions do guarantee us certain specific things. And I do think that in this 2020 AP exam, they will kind of focus heavily on understanding why we use certain conditions. All right, ladies and gentlemen, that is all for today. If you have any questions, always feel free to ask. Take care. Bye.